All right. Okay, so it does. I don't think so.
You can move it if you just slide over it. Yeah, perfect sense.
All right. Magic. All right. Recursion. All right. Okay, so we're going to continue with approximation algorithms, and in particular, you know, if you after your PhD go out and get an industry job, then what I'm going to say in about the next 45 minutes is probably the most applicable part of this course to the rest.
You should have done this before. You have announced it, I done it.
So we're going to be talking about integer linear programs, and things surrounding that, in particular applications to approximation algorithms. You know, that part is then less applicable to industry life. But the first part is so we've seen a particular kind of optimization problem so far, namely optimization problems on graphs, where I give you some input, let's say a graph, and then your task is find some set of vertices that maximizes some objective function of the graph and the solution that you provide. And so, for example, the size of the cut. So you want to either minimize or maximize the size of the cut. We also discussed the independent set problem, where again, input was a graph G, and the task was to select a set of vertices that was feasible. In particular, there were no edge between any pair of vertices that you selected, and you're trying to maximize some objective function, which is the size of the vertex sets that you selected. Now let's turn to a type of optimization problems that are not on graphs, but still have a similar flavor. You're getting some input. Based on that input, you want to make some set of decisions so that those decisions are feasible. They satisfy some set of constraints, and subject to being feasible, they optimize some objective function. So trying to be a little bit more concrete, your job is to set n integer variables. So the first part of the input to an integer linear program will just be a single integer n that tells you how many variables you have. Then you know that your variables are x1 through xn, and your task is to assign integer values to x1 through xn optimally. Oh, assigning them optimally, now you need to know something more, right? Subject to what are you trying to do? Suppose I also give you integers, c1 through cn. So, and your job is to, either maximize or minimize c1 times x1 plus c2 times x2, etc. Of course, so far, this problem seems very silly, because now suppose the coefficient of x1 is positive, you should just set x1 to be something that is as large as possible and don't care about anything else, and you got your infinite objective function value. So there is something that constrains how you are allowed to set your xi's, namely, you are required that your xi's satisfy a set of linear inequalities. These are called linear constraints. So these can be on the form, 5x1 plus 3x2 minus 10x3 is less than or equal to 8. 2x1 plus 3x2 equals 5. x5 is greater or equal to 0, etc. Right? In particular, every linear constraint can be specified by specifying these coefficients of the x's, whether you have less than or equal to or greater or equal to, and then the right-hand side. Yeah. So integer linear programming, what it's about is that I tell you the number of variables. I tell you a linear function to optimize. A linear function is just a function on the form, you know, the sum over all I from 1 to n of ci times xi, where ci's are constants that have been given and subject to linear constraints. So I give you as input all of the aij's and the bi's, and whether you have inequality in one direction, the other direction, or equality. And now your task is, please set the xi's such that all of the inequalities are satisfied, and subject to all of the inequalities being satisfied, that the objective function is either maximized or minimized. So that's known as an ILP. We assume that our inputs are all constants now, or I mean, like they're all not variables, right? So they're given to us as input, and that these are all either integers, so in Z, or rationals in Q. And now let me throw this at you. I claim that it doesn't really matter whether we demand that they are integers or rationals. We might as well we might as well say that they have to be integers. Why? Yeah, so basically if they're rationals, then all of them have some denominators. If you multiply both the objective function and the constraints out with the least common multiple of all of the denominators, right, then everything becomes integers. But you know, the least common multiple of all of the denominators could be a really big number. Now, how big can it be? Well, it can't be more than the product of all of the denominators, right? Which means that the bit size of your number isn't more than the sum of the bit sizes of each one of your denominators. So if all you care about are if you only care about polynomial factors, then we don't really need to distinguish between integer and rational coefficients, which is what we're going to be doing here. Because what we care about so far is are going to be running times that are polynomial in the size of the input. So now what is the size of the input here? If n is the number of variables and m is the number of constraints, that's what we're always going to be using. So n is variables, m is constraints, and big capital M is the biggest value of a number, let's say an integer, either numerator or denominator of your constants, then how many bits do you need to encode your input? Well, n times m, yeah, because you have that many numbers, times however many bits you need to encode one number, which will be log m. So little n times log big M is the size of your input. The size of your input instance. A little bit of terminology. A feasible solution is an assignment to the variables that satisfies all of the constraints, right? A solution can be, if I give you an assignment, it might satisfy all constraints, it might not. If it satisfies all constraints, I'm going to call it a feasible solution, right? The value of a solution is, you know, what you expect it to be. You plug it into the objective function, you see what number comes out, that's its value. All right, now given the definition of feasible solution and the value of a solution, anyone cares to guess what is an optimal solution to an ILP? Yeah. So it is a feasible solution so that no other feasible solution has a better value, right? And the optimal value is the value of an optimal solution. Now notice that an ILP does not necessarily have an optimal value or even a feasible solution. if I tell you that here I have just one variable, x1, and I have constraints x1 is greater than 5 and x1 is less than 4, then there is no x1 that satisfies it. So then we're saying that the ILP is infeasible because there aren't any feasible solutions. It might be feasible, but not have an optimal value for another reason. Any ideas? It can be unbounded, right? If I'm saying maximize x1 subject to no constraints at all, or x1 is greater or equal to 0, then I can choose x1 as large as I want and get as much objective function value as I would like. And then, of course, there is no optimal value. So when I give you an ILP instance, right, what you want to know is it feasible? If yes, is it unbounded? If no, what is the optimum value? Yeah. And most of the time when we're faced with ILPs, especially ILPs that sort of come out from other applications, it is sort of obvious that both it is feasible and that it has an optimal value. Because if it comes from some sort of, if this comes from some application that's encoding some resources, you don't have infinite number of any given resource. So basically, if you do, you probably modeled your real world incorrectly. Okay, so this is what your input looks like. The task is to compute an optimum solution, determine whether it's infeasible or unbounded. And let me reiterate that the size of the input is n times m times log of the maximum value. Okay. We already observed that with respect to polynomial time, we may just well assume that all inputs are integers. We might or might not do it later. Here's another one. Without loss of generality, all constraints are either less than or equal to or greater or equal to constraints. So there's no equality constraints. So why is that? Like from the perspective of polynomial time algorithms to solve ILP, I claim that they're not allowing equality constraints makes no difference. Exactly, right? So suppose I have 5x plus 3, like 5x1 plus 3x2 equals 5. I can replace that by two constraints. One like greater or equal to 5, the other one less than or equal to 5. And now that doesn't change the set of feasible solutions, nor the optimum value, like nor the objective function value. And doing this to all of the equality constraints will increase the size of the ILP by a factor at most 2, right? One constraint becomes two constraints. And this is why I say that from the perspective of polynomial time algorithms, doubling the size of your inputs doesn't really matter. Yeah. Okay, so now that we're only using less than or equal to or greater to equal to, I claim that it's in fact enough to only look at less than or equal to constraints. Yeah. Just multiply by -1 and the inequality is going to turn in the direction that you want. Okay. So here is the thing that is practically relevant, or first thing. And this is that there exist solvers out there that are going to solve ILPs ridiculously fast. So in particular, if you have some optimization problem and you can phrase it as an ILP, then you can give it to a solver, and with very high probability that solver is going to come back to you with a good answer to your problem. You wouldn't believe the number of times that people design algorithms for things and make computer programs and spend a lot of effort in situations where you might as well have just formulated this as an ILP, give it to a solver and just get back the solution. So this is a good thing to know. Like whenever you have an optimization problem, this is the baseline. Yeah. So that's the good news, and here's the bad news. The bad news is that ILP is NP complete. So this is one of those weird problems which very often are solved very fast in practice, but on the other hand, in theory, cannot always be solved to optimality in polynomial time. Of course, what does this mean? It means that when you have your application and you make your ILP and you feed it to the solver, there is always a non-zero chance that it's just going to run forever. By forever, I mean an exponential amount of time, but if you feed it, 10,000 variable ILP, that is isomorphic to forever. And you don't know whether it's eventually going to give you a solution or not. So we've looked at some problems. Let me, warm up your NP completeness muscles. So remember the clique problem? So let's, given a graph, find a set of vertices such that every pair of vertices are adjacent. Now, the independent set problem is you want to find a maximum set of vertices so that no pairs of vertices are adjacent. In the vertex cover problem, I give you a graph and I ask, give me a vertex set of smallest possible size, or of size at most k, so that every edge has at least one endpoint in the vertex cover. Okay, if you're allowed to assume that clique is NP complete, can you first prove to me that independent set is also NP complete? And then, assuming independent set, show it to me for vertex covers. I'm sure some of you have already seen this before, so I'm going to give you 20 seconds to think about it. And now here's the rule. By the end of those 20 seconds, if you haven't seen this before, you will have first priority to answer. So this is like, okay, so if you figured it out while you were sitting here, please raise your hand and answer the question. All right, so that was about 20 seconds. Okay, so if we assume that clique is NP complete, how would you show that independent set is? I'm assuming, okay, so most people, it's okay, now people who have seen it before are allowed to answer. Take the complement graph, right? So a clique in G is an independent set in G complement and vice versa. So complement means you flip every edge to a non-edge and every non-edge to an edge. That means that if I had a clique in my original graph, it becomes an independent set, right? And every independent set in the complement is a clique in the original graph. Yeah, so here is the picture. If I have a triangle in my original graph, when I complement it, it now becomes an independent set of size 3. And every independent set in the complement is a clique in the original graph. Okay, great. Now, what about independent set to vertex cover? You look at the same graph, right? Every vertex that is not in the independent set should be in the vertex cover and vice versa. So here's the picture for that, right? And so here is one that maybe fewer have seen. In the set cover problem, input is a universe of elements and a bunch of sets, so a family of sets over the universe. And the question is, give me the minimum subfamily such that the union of this subfamily covers the entire universe. So you can think of this as the elements are types of stamps, and then you're trying to collect one of each type of stamp. But then when you go to the post office, you can only buy several types at a time. So there's like multiple packages that you could potentially get. And then you get different types of stamps at the same time. And then you ask, what's the minimum number of packages that you should get in order to get at least one of every type of stamp? Yeah. this reduces from vertex cover in a bit of a funky way. Now, the vertices become sets. The edges become the elements, because in vertex cover, you're picking vertices to cover all the edges, right? So if you're picking vertices to cover all the edges, in set cover, you're picking sets to cover all the elements. So the edges become the elements, the vertices become the sets. And the set contains an element if the vertex was incident to the edge. Yeah. Okay. All right, so now, any one of these problems we could reduce to ILP in order to show that ILP is NP-complete. Let's show that ILP is NP-complete by reducing from vertex cover to ILP. Okay. So in vertex cover, input is a graph G. The task is to find a set of vertices of minimum size such that every edge is covered. Right. Now, why is vertex cover hard? Well, you have n vertices. For each one of them, you have to make a decision. Yes or no. Yeah. So you have exponentially many possibilities for how to make those decisions. So now, when you go to whenever you have an NP-completeness reduction, what you have to think is, how do I encode the decisions made in one problem in the other problem? And in ILP, your decisions are sort of obvious. There's you have variables, which value should this variable be? So now we need to translate the question, is this vertex in or out, to a which value should this variable get? And the most naive way of doing that is to say, well, for every vertex in the graph, let's have a variable that's 0 if the vertex isn't in the vertex cover, and 1 if it is in the vertex cover. Yeah. So how do we encode this? Well, for every vertex G, let's make a variable xv. And how do we enforce that it is between 0 and 1? Well, we make two constraints. Xv is greater or equal to 0, xv is less than or equal to 1, and xv is now required to be an integer, so we only have two options for where it should be, 0, 1. Excellent. Now, what are we doing here? Well, we're minimizing the number of vertices in the vertex cover. What does that translate to in our objective function? Well, we want to minimize the number of variables that are set to 1, which is known as minimizing the sum of the variables. Right? And now, finally, for every edge of the graph, we want to make sure that at least one of its endpoints has been covered. Okay, so how do you encode that as a linear constraint? Yeah. Yeah, so for every edge UV, we make a constraint that is XU plus XV is greater or equal to 1, right? So this is what this looks like. Yeah, and now this is what is called an ILP formulation of vertex cover. I mean, not only is the original instance a yes instance if and only if the produced instance of ILP is a yes instance, there's even a stronger relationship. In particular, every vertex cover of your graph corresponds to a feasible solution to the ILP that you made with the same value. And every feasible solution to the ILP that you made corresponds to a vertex cover with the same value. Yes, I'm not going to prove this. It should be fairly easy to see from the definition. If not, then ask, either now or in the tutorial. Okay, so, we showed how to reduce vertex cover to ILP, and this was fairly easy, right? And this fact that it is easy to reduce things to ILP, coupled with the fact that the solvers actually work great for ILP, is an important life lesson. If you ever need to optimize anything, right? All you need to do is, well, formulate it as an NLP, feed it to your solver. Chances are you're going to get an answer. Now, as a theoretician, of course, we are then still not happy because, okay, you formulate something as ILP, you can't do anything with it in polynomial time. enter a miracle. Miracle is called linear programming, which is the same as integer linear programming. So I still give you as input a bunch of constants, like n, how many variables I have, a linear objective function, linear inequalities as constraints. Let's say still all of the coefficients are rationals. But the only difference between ILP and LP is that now the solver is free to choose values for the variables that are arbitrary reals as opposed to arbitrary integers. Okay, so linear programming is just integer linear programming, but without the integer. So you can pick, so now you're not constrained to only picking integers as solution, you can pick arbitrary reals as solutions. And the miracle theorem is that linear programming actually can be solved in polynomial time in the size of the input, right? So if I feed the solver an LP, so a set of constraints and an objective function, then in polynomial time, in n times m times log the biggest number, you're actually going to get out a optimal solution to your linear program. Okay. So for every ILP, there is a corresponding LP relaxation. What does it mean? If I give you an ILP, right? It's an objective function and a set of constraints, and I'm asking you, give me an integer solution. I can treat the same input as an input to linear programming instead. Yeah, because the set of inputs is exactly the same. So the LP relaxation of an ILP is just the same input instance viewed with new glasses, namely the real variable value glasses. And here is a nice a consequence of this is that every feasible solution to an ILP is a feasible solution to the corresponding LP. Yeah, because every integer is a real number. That's a deep insight. So as a consequence of that, for every minimization problem, you know, the opt ILP is always either greater than equal to or less than or equal to the optimum LP value, and the same for the maximization problems. Okay, now I want to check whether you guys have been awake. In which direction should the inequalities go? Okay, let's do a show of hands. Okay. So for minimization, how many of you think that the inequality should go to the left? Like opt ILP is greater or equal to opt LP? Okay, less than or equal to? Okay, greater or equal, okay, you're awake, good, okay. And then I think you're going to guess that for maximization, it should go in the other direction. And now let's sanity check. Well, if I give you an optimum solution to the ILP, then that is a feasible solution to the ILP, and therefore it is also a feasible solution to the LP. And therefore, the LP might have a solution with even smaller value. Yeah. So for minimization, opt LP is greater than or equal to opt LP, and for maximization, the same argument gives you the inequality in the other direction. All right. We can formulate any problem we want as an ILP, and for any problem we want, we can turn the ILP into an LP, and we can feed it to our solver. We saw one ILP already for vertex cover, right? So you have a hammer, you have a nail. Let's apply the hammer to the nail. What if we solve the LP relaxation of the vertex cover ILP? Yeah. So what happens if I take a graph, then I make a variable for every vertex. I say, well, it has to be between 0 and 1. I make a variable, I make a constraint for every edge. Yes. So for every edge in G, xu plus xv has to be at least 1. And now I tell my LP solver, please solve this. Right? Now, if I'm really, really lucky, and the LP solver comes back and gives me values to the xv's that are all integers, yeah, so either 0 or 1, perfect, right? Then I have actually an optimum vertex cover to my to my original graph. Okay, so now the question is, does there exist graphs where no optimum LP solution assigns integer values to the vertices? Could it be true that for every graph, the optimum LP solution is always integral? All right, so hands up if you think it's yes. The answer to this is yes. All right, hands up if you think it's no. Pardon? Is it possible, right, or is it true that for every graph, if I take the vertex cover LP, then there exists an optimum solution to that LP that only assigns integer values to the variables? It's not possible. For example, an odd cycle, the simplest odd cycle is a triangle. So let's look at the triangle. Well, I claim that the optimum solution to this ILP is to assign 0.5 to every vertex. Now you can check that every edge is covered because, you know, the two endpoints have size 0.5. 0.5 plus 0.5 is 1, so every edge is happy. And you cannot do better. In particular, the sum of these two vertices because of this edge has to be at least 1. Yeah, and the top vertex has to be at least 1 minus the minimum of those two. So you'll always have to be at least 0.5. So the sum of all three always has to be at least 1.5. So this is the unique optimum solution to the triangle. Okay, so I solve the LP and it gives me this nonsense answer. This vertex is half the way into the vertex cover. Yeah. Okay, what to do? I don't know, it was a pointless idea. It was a good attempt, okay, but yeah. Why is this the only optimum? So suppose, I mean, okay, so first there is full symmetry here, right? So suppose I did 0.4 here and 0.6 here. Well, if I do 0.4 here, then I have to do 0.6 both here and up there. Yeah. So if I decrease this by epsilon, I have to increase the other two by epsilon, so I lose 2 epsilon. Okay. Well, you know, what do we? It's fairly often when we get some fractional number and we don't like it, we want an integer. So what do? You round to the nearest integer. Yeah. Okay, then let's do. So let's round our LP. So if you had 0.5 or more, you put it to 1. If it was 0.49 or less, you put it to 0. Okay, now this is a non-trivial statement. I claim that, I mean, this of course now corresponds, this is a solution to my LP. It might or might not be a feasible solution, but it corresponds to a set of vertices, right? I look at the vertices who are 1 after rounding. And I claim that this is actually a vertex cover. Why is that? Well, so first question is it a vertex cover? And the second is, how does the size of this thing compare to the size of a minimum vertex cover for the graph? So the first one is, well, for any edge, UV, right? Either U is at least 0.5 or V is at least 0.5. So one of them is going to be rounded up. Yeah, at least one. I found a vertex cover. Excellent. Yeah. Now, the question is, how good is this set S that you found? Well, the size of S is equal to the sum over all vertices of the starred variables, right? Like the starred are the ones after we rounded up. Yeah. Okay, now here is another interesting observation. If I take a real number between 0 and 1 and I round it, then I multiply it by at most 2. Everything 0.5 and up goes up to 1. That multiplied by at most 2, and everything less than 0.5 gets multiplied by 0, right? So the sum of the xv stars is at most the sum of the xv's times 2. But what is the sum of xv's? That was the objective function value of an optimum LP solution. Yes? So this is at most 2 times opt ILP. But what do we know about so this is at most opt LP. But what do we know about opt LP versus opt ILP? It's a minimization problem. So opt LP is at most opt ILP. So this is at most 2 times the optimum of ILP, which is equal to 2 times opt, which happens to be 2 times the size of the optimum vertex cover for this graph, right? So this is, in fact, a factor 2 approximation algorithm for vertex cover, right? Take your graph, turn it to an ILP, treat it like an LP, take the solution, it's fractional, so potentially nonsense, but round it. More than 0.5 or more, put it in your vertex cover. It's guaranteed that it will be a vertex cover because every edge is covered. And you didn't, when you rounded, you didn't increase the value by more than a factor 2. Therefore, it's a 2 approximation because the optimum to the ILP is less than or equal to the value of the optimum vertex cover size. Okay. Any questions to this? Okay. Now, notice that this is a fantastically generic scheme because, you know, ILP is so expressive that just about any of your favorite problems, you can formulate it as an ILP. Right? Then whenever you have an ILP, you can treat it as an LP and feed it to your solver and solve the LP relaxation. And whenever you have an optimum solution to your LP relaxation, now things become tricky. You can start trying to round it. But here, the obvious rounding works, right? Like thresholding at 0.5 goes up and down. That turned out to work. That's not going to work for all of your problems. Well, we're going to see one where it doesn't work in 5 minutes or so. Interesting. Live broadcast to Zoom has stopped due to attempted to start to an invalid broadcast session. It's too bad that Neil isn't here. Let's see, let me try again. I'm excellent. I'm disconnected from internet. Haha, okay. This is what happened, and now all right. Okay, I think we're back. Yes. And then I need to do this thing. Okay. So no, we're not back. Interesting. Come on. The screen sharing ended unexpectedly. You need to reboot this device. All right. Take 5 minutes while I reboot this device. It kicked me off. It kicked me off the internet. And then when I tried to go back to Zoom, it says that I have to reboot because Zoom is unhappy.
Like they're just not used to it. Zoom में घुसाना उनको, ये Zoom में नहीं घुस पाते। भाई अनंत, तुझे क्या पता नहीं है सब कैसे करते हैं?
Let's see. Let me just connect. Okay, I'm connected to internet. Oh, this is the wrong one. Google. It's gonna be fast. I'm basically done already.
Now lecture?
No. I'm done with logging in. Almost. Where is it? There we go. But Neil isn't here, right? Second. Because I don't know if I'm still co-host because now. Okay. Well, we'll see. Okay. Yeah, because now I need the host to log me in again. This is I need someone to log me into the Zoom room, like let me into the Zoom room again. Okay, yeah. You just have to let me in. Zoom.
Okay. Zoom logged me out, so I was wondering what happened. And I didn't. Okay. I'm just a bit nervous because it says start as if it's going to.
You can get the post control to that one.
Huh.
So then you can control.
You have to.
Sorry, I'm going to avoid running away.
All right, it looks like we're back.
So do we need
I guess we have to log out from that and so.
Okay. So the only problem is, like this is connected to the YouTube live stream.
Oh, okay. Okay, yeah, understood.
All right, so we're back and we'll start again in 1 minute, just so that people have time to.
Like say we can do that.
You can try to figure it out. The reason it's tied to my Zoom is because it's also connected to the YouTube live streams. I don't know if changing it to this guy will disrupt that in some way.
Let's figure that out tomorrow or yeah.
But you can just log in with my account and I can copy it.
But if I log in with 2 accounts, with 2 devices, it will cost.
No, I am logged in with 100 devices. So
Okay.
it's fine.
The next session.
Yeah. Sure.
Pardon?
I have a question. So is the length of the formula, that is the equation, does not dependent, the time is not dependent on.
Well, so it's this. So I mean, the length of a linear constraint is always upper bounded by the number of variables.
Yes,
Yeah.
but
So so the question is, if it was shorter, would it be faster? Not the way it is stated, right? But it works much faster than the stated running times. Yeah.
Because it has to guess less number.
Yeah. Yeah. I mean, I don't think the proved bounds depend on the number of non-zero entries, or at least not the ones that I cited. There are algorithms that follow that potentially do. But in practice, of course, it depends. Yeah. All right, so let's start again. So where we were before the technology interruption was to think of this general scheme that you could apply to any problem to turn to use ILPs and the LP relaxations to get an approximation algorithm. So whatever problem was, if you could just formulate it as an ILP, then you solve the corresponding LP. And then once you have an LP solution, now you have to find some clever way of taking this potentially nonsense fractional answer into a sensical integral answer. And in the case of vertex cover, of course, it was easy because you could just round up. That's not going to be the case in general, but very often one can find clever ways of turning a fractional answer. And then you're trying to balance two things. On one hand, you want to make it integral so that the resulting integral solution is still feasible. That's the first thing. But on the other hand, you want the objective function value of the integral solution to not be much worse than the objective function value of the fractional solution you started with. So those are the two trade-offs, the two things that are trading off against each other when you are trying to round an LP solution for an approximation algorithm. Okay, now here's a question. Wasn't this a randomized algorithms course, right? And I haven't told you anything randomized. And now let's move to the randomized part and look at the set cover problem. So I've already mentioned it, but let me reiterate it to you. So input is a universe of size m and m sets. Let's call them S1, S2 up to Sm. These are subsets of the universe. And your task is to buy the minimum number of these input sets so that together they cover the entire universe. So formally, we're finding a family F prime, which is a subfamily of F. So for every set in F, you either pick it or you do not pick it, so that you minimize the number of sets that you do pick, and so that the union of the sets that you do pick is all of the universe. So I'll define the coverage of F prime or C of F prime to be the union of all the sets in F prime, and I want C of F prime to be the entire universe. So that's my problem. This, of course, encodes vertex cover, as we observed previously. If we turned edges into elements and vertices into sets, wherever the set corresponding to a vertex contains all the edges incident to the vertex, then the minimum size set cover for this set system corresponds precisely to a minimum size vertex cover to your original graph. All right, let's try to go through this scheme for set cover. Well, an ILP formulation, very reasonable. Your decision is for every set, should you pick it or not pick it? So let's have a variable for every set that is again between 0 and 1. Okay, now what should the objective function be? Some of the variables before, right? And are we minimizing or maximizing it? Minimizing, right? Because we want to pick as few sets as possible. Okay, and now what are the constraints, right? We want the total coverage of all the sets we picked to be the entire universe. So a suggestion for constraints that will enforce this. Yeah.
For every element,
Yes.
the sum of x s's
Uh-huh.
that this element is in S should be greater than or equal to 1.
Yes. So for every element, we should pick at least one set that contains that element. So if we look at all the sets in the input that contain that element and the variables corresponding to it, at least one of these variables should be at least one. Yeah. So in particular, for every U in the universe, if we sum over all sets in the family such that U is part of that set of XS, then this should be at least one. And of course, we don't want to be able to pick sets like -1 picking a set. So if we say that XS is at least 0, we could also enforce that it's at most 1, but we don't have to. Why not? Exactly. So no, like when you feed it to the solver, the optimum the optimum solution is never going to set any variable to more than 1. If I set it to 1.1, then all of the elements contained in that set are covered, they're even over covered. So even if I decreased it to 1, I would still be covering everything and my value is smaller. Yes. So I can enforce it, I don't have to, doesn't matter. Okay. So this is an ILP. We can't solve the ILP, but we can solve the LP. So we do, and we got an optimum solution to the LP relaxation. Yeah. What does it mean? Well, for every variable, you got some number. You pick this, you pick 10% of this set, you pick 20% of this set. Yeah. Seems like nonsense again. Let's try to do the rounding as before, right? Like if it's 0.5 or more, you round it up. If it's less than 0.5, you round it down. Yeah. Is this always going to work? No. Why? An element can be present in more than 2 sets, right? So suppose I have some element and there is a 1/3, 1/3, 1/3. It used to be covered, but all of them get rounded down to 0. And now this guy isn't covered anymore. Yeah. So this simple rounding of rounding up from at 0.5 doesn't work. Okay, but does that mean that like nothing works? I mean, notice that this argument for 1/2, I could generalize it to any constant, right? Like if some variable is covered by 10 sets, each with value 1/10, yeah, then if I threshold it at 1/9, then all of these guys go down to 0. Yeah, and this would work for, I mean, this kind of counterexample will work for any fixed value. So look at the element that occurs in the max now. Okay, and then what? Yes. So that's okay. So this is a good point. Look, you can look at the element that occurs in the maximum number of sets, and you never need to. You can set the threshold to be 1 over that. Yeah, and that will give you an approximation algorithm with ratio f, where f is, you know, this maximum frequency of an element. But you know, that can be as big as m in the worst case. So now what we want is to have something that is small even when n is large. Yeah. We're going to do the following thing. So in particular, there are instances where the algorithm you suggest is the best algorithm to run. But if you're not willing to assume that the frequency of all elements is bounded, then you have to do something else. So since we want to do something randomized, here is a funny thing. We have some numbers between 0 and 1, right? Every number between 0 and 1, I can treat it as a probability of something. Now, you know, if XS was 1, that would be a pretty good indicator that I should include S into my solution. And if it's 0, then I shouldn't include it. Yeah. So it's a pretty reasonable interpretation that if I have XS equal to 0.1, that like, oh, this set is 10% in my solution, let me include it in my solution with probability 10%. Yeah. So now what I'm going to do is I'm just going to individually, for every set in my input family, I'm going to look at what is XS is, and I'm going to throw a biased die or a biased coin. Comes up heads with probability XS, tails 1 minus n. If it comes up heads, then I include it in my solution. Now we should ask the same kind of questions that we did for vertex cover. The first one is, well, how big is this family going to be? Right? We do find some family of sets in this way. How big is it going to be? And the second is it going to cover U? Yeah. And notice that f prime is now a random variable. So, you know, it doesn't have, it could be everything. It could be nothing. It could cover all of you. It could cover nothing of you. So all of these sort of statements, how big is it? Does it cover you? Have to be probabilistic statements, right? Like the probability that it is at least this big is at most that. The probability that it covers is, right? So these are the kind of statements we want to make. And for the question, how big is it? We already have a tool to analyze it, namely expectation and Markov inequality, right? So let's do that again, right? So let's compute the expectation of this set f prime. All right, what are we going to do? The thing we already did, method of indicator variables. Let's make an indicator variable that is 1 if the set gets put into your family, 0 if the set is not in your family. And now notice that the size of your family is just the sum of the indicator variables. Yeah, which means that the expected size of your family is the expected sum of the indicator variables, which happens to be the sum of expectations of indicator variables. Right? Expectation of a sum is the sum of the expectations. By linearity of expectation, maybe you're starting to appreciate the dark magic now. And now the question is, what is the expectation of each one of these random variables? Okay, so what is the random variable? So ys is 1 if I put the set in the family, and 0 if I didn't. Yeah? And if you remember from previous lecture, the expectation of a 0, 1 random variable is just the probability that it's 1, right? Because 1 times the probability that it's 1 plus 0 times the probability that it's 0. Yeah? Okay, so now what is the probability that ys is 1? It's xs, right? Ah, so this is nothing but the sum of all the xs's, but that is just the value of the LP solution that we had, which is opt LP. Yeah, so fantastic. The expected size of our family f prime is opt LP. Yeah? Couldn't ask for better. So for example, the probability that it's no more, that it's at least twice as big is at most 1/2, right? So for probability at least 1/2, it's a 2 approximation. Except, does it cover you? Ufta. Answer no, right? Let's think about this. So here is an instance, right? So these are the triangle. This is the triangle instance from the vertex cover, and I'll ask you to analyze it in the tutorial. Neil, did you see that? Yeah, okay. Right. In particular, for this particular instance, you know, the optimum solution picks each one of the sets with probability. It will set 0.5 on each one of them. Yeah? Like every set is picked 0.5, and then you ask, well, if you pick every set with probability 0.5 and you have many of these little triangles sitting next to each other, what's the probability that all of the elements gets covered? I claim that probability is actually exponentially low, but I'm going to let you prove that. Okay, so all right, we did this magic rounding, right? We did this magic rounding, and the size of the family turned out to be exactly what we wanted to be, but it doesn't cover it's not feasible. It probably doesn't cover the universe. But okay, I mean, it probably covers something, and maybe we can well, let's try to analyze what does it cover. Okay, so let U be your favorite element of the universe, just an arbitrary one. And I ask, well, what's the probability that this family F prime doesn't cover this element? Okay. I claim that it's this. It's for every set that contains the element, I shouldn't pick that set. I shouldn't pick this. I shouldn't pick this, right? So the first set, I don't pick it with probability 1 minus xs. The second set, I pick it with probability 1 minus xs prime for the next set, and so on. Right? So it's the product of 1 minus the variable value. Yeah? Enter the inequality again. Right? 1 minus xs is at most e to the minus xs. Yeah? And now we turn a product into a sum in the exponents. So this is e to the minus the sum over all sets in F that contain the element of xs. And what do we know about this sum? It's at least 1. Yeah? So in particular, this is at most e to the minus 1, which happens to be 1 over e. So what does that tell us? It tells us that for every fixed element, the probability that we didn't cover that element is at most 1 over e. Well, I mean, it's so you cover a good fraction of the elements, but far from all. Okay, like what can we do? Okay, so here is the next idea. Suppose I give you this xs, right? And then I do this random process. I find the family F prime. It covers some part of the universe, but not everything. If it doesn't cover everything, let me find another one. Let me just do the whole rounding process again. And I don't solve the LP again, I just round again. And I get some family F2. I do it again, F3 also, and I do it for t times, for some t that I'm going to choose cleverly. And then I hope that the union of all of these families covers all of the universe, right? Recall, what we're trying to do is a trade-off between the size of the family that we output and the probability that it actually covers everything. Yes, so when the family was small, it didn't cover everything. Okay, let's make it bigger and hope that it does cover everything. So what we're going to do is we're going to pick, t families, F1, F2, F3, all the way up to Ft. Say F prime is the union of all of these. And now we ask, okay, what's the probability that F prime covers the universe? And again, now what we're going to do, so how much bigger will F prime be? Well, the expected size of F prime is the sum of the expected sizes of the Fi's. Each one of them is opt LP. So again, by linearity of expectation, this is nothing but t times opt LP. Yeah? If you take t families, each one of them expected size is opt LP. Expected size of the union is at most t times opt LP. Okay, now here's the interesting thing. If I take a fixed element u, what's the probability that my big F prime doesn't cover u? Well, the first family that I pick shouldn't cover it. The second family that I pick shouldn't cover it. The third one, so the first one didn't cover it with probability 1 over e. The second one with 1 over e. The third one with 1 over e. And this all happens independently of each other. So the probability that F prime doesn't cover u is e to the minus t. Yeah. So now, let me do some math. Let me crunch it. Let me set t to be the natural logarithm of e times m, whatever. Okay. Now, notice the expected size of F prime is opt LP times ln of e times n. So this is a log n approximation algorithm if it works. Yes. But what is the probability that it doesn't cover u? Is that it's e to the minus ln en, so it's 1 over en. Yeah, so if I pick a fixed vertex element, the probability that my family doesn't cover that vertex is at most 1 over En. Now comes the next magic bound, which is called the union bound. It's like another thing that you learned in your stats class and didn't think much of. Yeah, and this is the probability that you don't cover the entire universe is at most the probability that you don't cover the first vertex, plus the probability that you don't cover the second vertex, plus the probability that you don't cover the third vertex, and so on. And so it's at most f prime doesn't cover u1, plus that it doesn't cover u2, and so on. And this is the fact that we are allowed to do this is both important and non-trivial. It's non-trivial because these events could be highly dependent on each other. Yes, but the union bound holds in general. For any pair of events, the probability that one of the two events happens, at least one of them, is less than the probability that this happens, plus the probability that that happens. So, we have n bad events. Each one of them happens with probability at most 1 over En. Well, then the probability that at least one of them happens is at most 1 over E. Yeah, n over En is 1 over E. So, with probability at least 1 minus 1 over E, the family that I output covers all of the universe. Now notice, if I want to have constant success probability, or I want to have success probability 99% without increasing the size of my solution, all I need to do is I need to run the whole thing a few times and then see if any one of them actually ends up covering the entire universe, because each run will cover all of the universe with constant probability. So this is a ln n plus 1 approximation for set cover that runs in polynomial time. Turns out that this is tight. I have an ask socket here, which is that, so the first time when it was showed that you cannot do better than a ln n approximation, like a 0.99 ln n approximation, this was not under the assumption, under the assumption that p is not equal to np. It was like then np is a subset of quasi-polynomial time, something. But has it been shown since then? No.
It's not, but you can show there's some constant times log n not possible on this p.
Okay.
But that is not one.
Okay. So it is tight, but under a stronger assumption that p not equal to np. And if you're only willing to accept p not equal to np as your assumption, then it's c log n for some constancy. You cannot do better. So it's still, very close to optimal. Okay, and I think that is actually all I had for today. Yep. Questions? Counterexamples? No? All right. It's exactly the same approximation ratio. So the greedy algorithm, the one that takes, so the most bang per buck. So you take the set that covers the most elements, you pick it, then you remove it, and now you take the set that covers the largest number of yet uncovered elements, you pick it. You can show that that is also a ln n approximation. Yeah. So now I have to make sure that, okay, so if the frequencies are small, right? So if you cannot, if no set appears more than f elements, yes, then you get an f approximation by this stupid rounding. Yes, like just thresholding at 1 over f. And that is known to be close to optimal. So I'm not sure whether some version of this algorithm can be shown to give an F approximation. Yeah, with a little bit of tweaking, yeah. But that is basically what the limit is, because there are known hardness results that stop you from doing better than that. Any questions from Zoom?
The same analysis can also show if the set size bounded by some numbers, then the approximation will improve on T.
Yes. All right, so tutorial starts in 45 minutes.